Good morning, everyone. I'll be talking briefly about some ongoing research effort with New York City Transit and Con Edison. So the talk is more on the problem definition and the methodology, and less on the final outcomes and results because we're still in progress. The Metropolitan Transportation Authority is a large consumer of electricity, and New York City Transit alone consumes more than 75 or 80% of the whole MTA energy consumption. More than 50% of the New York City Transit trains, of the existing cars and all new ones, are regenerative braking capable. This gives us an opportunity to use this energy for energy saving, this regenerative braking energy for energy saving or energy recovery, peak demand reduction. These are the straightforward applications. In the literature, in some countries and some systems, they use them even for voltage and frequency regulations and other services to the grid. Even though the trains that are capable to use the regenerative braking produce the energy every time they brake or every time they decelerate, it doesn't necessarily mean that you will be able to put this energy on the third rail or on the line and make use of it. And the reason is that this energy is huge, and unless there is a load as close to the train that is decelerating, the voltage will go up, and the protection system will dump this energy into resistors as heat. So those are the systems in which people took the initiative to make the most benefit out of the regenerative braking energy. They will have to modify the system so that you make sure the conditions enable you to get the most out of the regenerative braking energy. And the most commonly used methods are these three methods. Timetable optimization, in which you have some real-time control and monitoring of the trains, and you want to schedule the trains such that whenever a train is decelerating, there is another train accelerating nearby, maybe at the same passenger station. And then you want to exchange the energy between the decelerating train and the accelerating train, and then you decrease you reduce the amount of energy that you need to get or you draw from the substation, creating some energy saving. The second method is energy storage based. In this case, you eliminate the need to synchronize the trains because you have some energy storage. Whenever a train decelerates, you charge your energy storage system. It could be battery, supercapacitor, or flywheel. There are test results for all these cases in the literature. And then when another train is accelerating in some other time, they don't have to synchronize at the same time. You will discharge your energy storage system, again resulting in energy saving and peak demand reduction. The third method is a reversible substation. Typically, the substation, or they call it the rectifier substation, which is the substation that gets the power from the main grid, and then you have the rectifiers, and then you feed your third rail, which is DC, the rail that supplies the trains. This is typically an uncontrolled rectifier, which means that it is unidirectional. It gets the energy from the main grid to the subway system, but not the opposite. So you could replace this rectifier with a bidirectional converter, or you could leave it as is and add another inverter in parallel. And in this case, you will enable the energy to go back to the main grid. If it's an energy storage-based solution, which is number 2, here on this slide, you can put the storage on board, so the train will be moving, carrying the storage on board, or wayside, on the track side, connected to the third rail outside the train. Each will have pros and cons, but in the literature, there seems to be consensus that wayside is better because you reduce the weight on the trains, and then it serves multiple trains. If it's on board, then it's for this particular train. If it decelerates, you store the energy in your ESS, and then this train accelerates, it takes the energy back. But on the wayside, it could be multiple trains. Con Edison and New York City Transit are both interested in exploring this opportunity and finding what the best solution could be for the system here, or if there is a need to do something to improve the utilization of this regenerative braking energy. So at this stage of this research, the main questions we are trying to address are what is the regenerative braking energy recuperation technique that will provide the value proposition for Con Edison and New York City Transit? And if we decide on one, what will be the optimal size and design and placement? And why these questions are not trivial to answer is because there have been some demonstrations, for example, for example, flywheel or battery put in the MTA system, and we look at the results, but there is no study that covers all the possible scenarios and all possible solutions and tries to address the problem strategically. So you have a way to decide in this particular location, maybe I should use this technique versus the other. So there's a lack of detailed and technical analysis upon which informative decisions can be made. And the other challenge is that we need to fully understand what happens now with the regenerative braking energy. And we need to develop models that are scalable enough and accurate enough to be able to tell us if we choose to do something, what should we expect on the actual system, so that we determine the value proposition. So when we started to look at this in the beginning, we started from scratch, the very basic, to develop the very basic understanding of the regenerative braking energy and how it works. So if you look at this free body diagram, you have the traction force, and this is what the motor will need to have in order to move on the rails. But you have some opposing forces. That includes the gravitational forces, friction, and aerodynamics facing the train. And when you combine all these forces, you can develop some simple equation to describe the traction force. Having this traction force, we can get into the torque needed at the wheels. So if we take this traction force, we multiply it by the radius of the wheels, and then we divide it over the number of cars, and then knowing that one car will not only have one axle, it will have 4 axles, then we can get the torque at the axle or the wheel, it's the same. And then I can get also the angular speed of the wheels. The torque at the induction motor is magnified with some gearbox. So if we take that into account, we can put here the gear ratio, 5 or 6, and then you'll be able to get the torque near the machine itself. From this, we will be able to get, so if we multiply the torque at the wheel by the angular speed, we'll get some mechanical power at the wheel. And then the total regenerative braking energy, if we assume for simplicity for this initial step that all these efficiencies are known and are constant, then we can have a formula for the regenerative braking power, which is this one. So as you will notice, it's a function of speed, the mass will have different variables. A common practice in the subway system is to accelerate at a constant rate and decelerate at a constant rate. It's not always like this, but this is how it should work. This is the practice, to accelerate at, for example, 2 point. Doing some coasting when you reach the maximum speed, and then when you start to decelerate meters per second constantly until you reach to the standstill. So if we make use of this piece of information and we come up with this simplified, like linearized speed profile, we can go back to this equation with this constant acceleration. And then we can calculate a more detailed, like, electric power curve. This electric power, I didn't call it regen power because it's really general. It's for during acceleration and during coasting and during deceleration. And from that, we can easily, of course, get the energy itself. So we can make use of this very simplified analytical model to look at the various parameters that may affect the regen energy, or the regenerative braking energy. For example, the frontal area affected the aerodynamic force resisting the train. It doesn't make much difference whether it's big or small. You can see here if you double the area, which is probably infeasible, but just for the sake of like knowing what is more influential on the regen energy, you'll notice it doesn't make much difference. The efficiency of the inverter is very important because all the energy has to go through it. So it's very important. The mass of the train is very important, which is probably a reason why when you have a heavily loaded train, you get more different energy than a lightly loaded train. And we see that when you look at the profile throughout the day. You can also look at other parameters like the inclination angle, whether the train is accelerating or decelerating at a flat surface or if there is some inclination. It makes a difference in the amount of energy. So what we are looking at here is this part is acceleration. During acceleration, you can see that the power is positive. So that as the train accelerates, it takes more power until it reaches to the maximum speed. But then when it reaches to the maximum speed and it starts to do the coasting, then the power is really minimal. If you're dealing with a simplified model like this, it will probably be zero, like the red line. And then during the deceleration, the power is negative, which means that the train is really producing the energy now. So these parameters that we just discussed are parameters that affect the amount that you could potentially produce. So the regenerative braking energy that the train will produce, but as I mentioned before, you cannot guarantee that this energy will be sent back to the third rail. So if you look at this graph on the left, this is a simplified graph in which a train is moving on the rail, and it's of course connected to the third rails through this shoe, contact shoe, and it is decelerating. So imagine this train is now decelerating here, so it's producing some regenerative braking energy. This energy will become distributed on the third rail in both directions, right? We can model this very simple scenario with a very simplified circuit. So this is the train. The train is producing some energy, and this energy will result in this current according to the previous equations. The rail itself has resistance, so we can model that with some small resistance here. And then there will be some other trains on the rail in both directions. Probably, let's say it's a passenger station, and you have a local train and another express train at the same station. Or it's a train going northbound and southbound, for example. So the energy that this train is producing may be shared with other trains. Now, we can model these other trains, the other loads on the system, as some Thevenin's or Norton's equivalent. So in order for us to send the current from this train that is braking to the rest of the system, in order for this regen to be high, the voltage here at node 1 will rise. Right? So in other words, if the train, that other train that is accelerating, while this train is decelerating, producing energy, is close, then there is a better possibility that it will take the energy. But if it's very far, the voltage here will rise. And the control, there is a limit for there is an upper limit and there is a lower limit on the voltage. So for example, the voltage here in the system here in New York City works, the rated voltage is 650. So it cannot go, for example, above 680 or 720, depending on what they set it up. In this case, when this regen energy is produced, in the beginning it starts to send it to the third rail, but then the voltage is rising. So what you need to do is to have on board some other way to dump the energy, and this happens often. So you have the energy, you produce the regen energy, but because the conditions on the line do not allow you to send this energy to the line, then you have to dump the energy through some chopper resistance. And this introduces a term that they use in the literature when people work on this field, which is the line receptivity. So whether your line is receptive to the regen energy or not depends on many things. The timetables, the braking strategy, like when will you let this chopper work, for example, the settings of the chopper, even the design of the chopper itself. All of these will affect the regenerated energy or the amount of regenerated energy that you'll be able to send to the third rail. So at this point, we were curious to know what is happening now in the system, in New York City Transit. So Con Edison with New York City Transit did a very interesting study. They shut down, they turned off the regen energy from the trains on one of the lines. Okay? And then they pulled up the data from the substations feeding this line, like previous data. And then they compared what would be the power coming from the substation if the train is regenerative braking energy capable or not. And this is the difference. So you can see that there is some peak demand reduction happening when you don't have when you have the regenerative braking energy enabled, and you have some shifting here. But it also gets you curious to know whether you can really improve this by having some other technique, like wayside storage, for example, or reversal substation. So with the previous model that we had, the analytical model, we get a very good first impression, but it's not enough really to draw conclusions. So we had to look for more detailed modeling. This is a very small segment of the line, for example. So you have here a scenario where you have two substations. They happen to be physically close to two passenger stations, but then there is another passenger station in the middle, for example. So we try to simulate and model scenarios like this with bigger systems, less systems. And when we have the model developed, we want to validate the model. And then after validating the model, we'll be able to, for example, put some wayside storage here and see the difference in the operation. And then we can decide which technique is better. So, for example, here, and if you look at this system, you need to model the train, you need to model the substation, you need to model the rails, for example. You need to model everything. So we try to develop these models, and we have the model developed, but now we are in the validation process. So, for example, the train looks something like this. You have the power coming here from the substation, which is two large transformers in that substation, rectifier substation, followed by two rectifiers for redundancy. And then the two rectifiers meet at some common DC bus, where you have some capacitor as a filter. And then you have the braking chopper, and then you have the three-phase inverter, and there is a speed controller and torque and flux controller. For example, we use MATLAB Simulink whenever a library is available and it's good enough. We just use it. Whenever we have to modify, we modify. So, for example, this is the speed controller. Very simple. You have the reference, and you have the actual speed, and it's just simply a PI controller with some torque limiter. So the PI controller with the speed as an input will yield the reference for the torque, and then the reference for the torque will go to the direct torque controller, which we use the blocks from Simulink. So it gets the torque and the flux as a reference, and then it also gets the current and the voltage, three-phase current and voltage, with some torque and flux calculator. It gets the angle, which goes to a switching table for an SV PWM inverter, a space vector pulse width modulation inverter. The torque and flux calculator are based on Park's transformation. So we converted the VABC to some DQ frame of reference for the voltage and the current, and then the difference will yield the torque and the angle. For the substation, as I mentioned, this is a simplified graph. There are some little details that are not really included here, but this is the main schematic of a substation, for a rectifier substation. It has two transformers. One of them is delta delta and Y delta, and some other auxiliary transformer to auxiliary loads in the station, and then you have the two rectifiers feeding the third rail. We have to put the transformer parameters, so there was a lot of data requests into this project. So we had to get the spec sheets for the transformer and filter parameters and all of these things in order to be able to model the substations. For the rail model, it's a simple idea. When the train leaves passenger station 1, for example, and reaches passenger station 2, the resistance drops here, decreases here linearly, and it increases on the other side. So we just had to model this because it affects the amount of regenerative energy and losses. So what we did is some two variable resistors on both sides for the traction, for the power resistance and for the traction resistance, because one of the traction lines is used for return current. So we have to model the resistance for that too. And we realized that by some basic controlled voltage source here, which just looks at the train position and the power supply position, gets the difference, and then we have the resistance per unit length. We multiply them, we get some resistance. This is the resistance now to be calculated. And then, as I said, just the voltage over the current will be the resistance. In order to do the validation, we acquired, well, I mean, with the help of Con Edison and New York City Transit, we acquired some data from one of the lines in New York City Transit where they had measurements on board. So we get the speed profiles with the current and power and the energy and everything, and we try to use that for validation. We're trying to get closer to the curve, but there is a big challenge here, is that yes, you have the data of one train moving, and the acceleration, deceleration, all of these, but you don't know what's happening on the third rail. So we try to model that with some uncertainty in the model, and then we try to add some load that we don't know about, and we try to change that load until we get closer to the actual results. And in this case, we kind of estimate that the load profile that created this matching will be representing the load on the third rail in that time, and any inaccuracy, of course, in the model. Once we have the model validated, so our next step will be to start modeling with wayside energy storage different technologies. For example, with the battery, this is the train current. This is one of the actual profiles. So if this is a train current, the green one, and we have some battery working at 1C, for example, providing this much current, the blue one, then the substation current will obviously drop. And then when you increase the C rate, what will happen to the power profile and so on and so forth. And then we can relate that to the lifetime of the battery and the cost, and then we can come up with the cost-benefit analysis that we're looking for. The same thing for the supercapacitor, the profiles will look different, but this is the step where we are right now, the validation and running these simulations with different storage technologies like the battery, supercapacitor, and in conclusion, the regenerative energy has the potential to provide peak demand reduction. At least that's what we're sure about. The detailed model has been developed, but we are still now in the validation process. We're trying to build more credibility and be sure that this model really represents the actual behavior. The validation models, the validated model, will then be used to decide about which recuperation technique should be used or should be recommended. And finally, I'll acknowledge the research teams. We have Mr. Andrew Reed from Con Edison, Mr. Tom Lamb, and Mr. Bruce Alexander from New York City Transit, and Mr. Keith Cummings from Dayton Brown. Thank you.